Oh, this is Mr. McMurray, and we are going to have a magnetic personality today, I guess. All right. Anyhow, we are going to talk about magnets. Okay, magnetism. We talked about electricity last week, and we said magnetism and electricity are like this. If you have one, the other one is there. You may not notice it, you may not see it, but trust me, it is there. Okay, so let's talk about this for a little bit. First of all, starting with magnets. The first magnets were magnetite, was a mineral that was found in the ground, and it was magnetic. And so they found that they took little slivers of it and floated it on water, on the surface tension of the water. It would line up according, always point the same direction, basically, because it had a north and south pole, just like a compass that we have nowadays, same general thing. Now we just have a little piece of metal in there that's been slightly magnetized, and then the Earth has its own magnetic field, and therefore it is basically a giant magnet. Okay, and this needle will always line up the same direction in that magnetic field. And the same would happen with a little sliver of magnetism. So they were called lodestones or leading stones because they would lead them in the right direction, which was good if you were a sailor out in the ocean, and they didn't have GPS and all this kind of stuff. So they very important things that they came up with. They were supposedly discovered by Magnus, who was a shepherd there, and hence the name magnet. And it was in the region of Magnesia, which, interestingly enough, not Philip of Magnesia, that's a whole different thing, but it had magnesium was discovered in that same area. But anyhow, and that's one of the main characteristics of magnets. Let's talk about magnets for a second, is how they're like electricity, which we've already talked about electricity and how it's a little different from gravity, but magnetic is more like electric forces in that it can attract things or repel things. Okay? And anyone who's played with magnets before knows this. Okay? So basically, if you get opposites, north and south poles next to each other, ouch, they will join together. They are attracted. However, if I flip one of these over, so now I'm doing like a north pole and a north pole, now they repel. And that's about, it's hard to keep them straight, but that's about as close as I can get. It's a very strong force, and trust me, it is not going to touch it. Okay, and so very real force. Notice that they do not have to touch each other to attract each other, all right, or repel. Okay, if I get them, I don't really feel the attraction until about right in there, and then boom. There's the closer they get, the stronger the attraction. In fact, these are strong enough magnets. You have to be very careful. They will slam. I almost pinched my finger earlier. You'll get little blood blisters, and if they're sharp, you can actually cut yourself pretty bad on these because the force gets really, really strong as they get closer. Okay, which, if you remember, we talked about with electricity, the distance between and gravity. The distance between them, once again, is d squared on the bottom of the formula, the inverse square law. So once I get them here, they may not do anything to each other. But once I get them within a certain distance here, then they will start having a force on each other. And the closer they get, the more it exponentially increases. Okay, so that's also like electricity. Okay, it has the inverse square law. They don't have to touch each other. They can exert a force, so we'll call them non-contact forces. They don't have to touch each other. Like when you push something, you have to actually touch it to push it. Okay, but magnets do not do that. They can do that from a distance. And just like electricity, they can attract or repel, if depending, once again, opposites attract and like repel each other. Now, question may be, how can we tell which end of a magnet is which? All right, now just for record, is there any difference between a north and a south magnet, a pole of the magnet? Oh, excuse me. Okay, and the correct answer is really no. Okay, just like the charges of an electron and a proton, is one positive and one negative. Well, they just knew that they were opposite and alike. It really didn't matter which one was which. They just picked it one way or the other, and that's how they did it. Now, if I have this magnet, I can get this. This is a magnet tester, and it tells you which pole it is. So if I get it close to one side over here, I'll see if I can turn that towards you and turn the magnet up on its side. And now we're not getting anything. Okay, so that means we're not doing it right, right? It will eventually, whoa, light up, okay? And it turns out that the north, it only does it when you get on the north side of it. So let me do this again. If I get on this side of it, that's the front one, which is north. And if I do it on this side, see if I can get it, you notice it's the second light or the bright light, which is south. Now, how does this one know which is north and south? Well, electricity and magnetism are related. So it has a battery in it, and depending on the direction the battery pick, it will always tell you which one is the north or the south. Now, if I do it on the side of the magnet, you can see that. But if I do it in the segment, it may not give me a very good reading. But if I get on this side a little bit, then it'll give me a south. If I get on this side a little bit, it'll give me north. Why? Because this side of the magnet. So in this case, the flat surfaces are the poles. Now they can do it either way. They can make the top and bottom on the two sides. You can make these two sides top, north and south, or in this case, the flat surface. This is the north and this is the south, or vice versa. Okay, I'll have to check real quick just to see which one's which, but there we go. That one is actually the north of the bottom button. So this north and this is south. Once again, is there any difference between north and south? Well, they're just the opposite of each other, so it doesn't really matter which one's which, but they do have poles. Now, if I were to take this magnet and break it into smaller pieces, which I'm not going to do because I like my magnets, okay, but I do have some here that have already been broken. Okay, they got little pieces. But notice that each one of those pieces still is attracted to the other magnets, and they still have a north and south pole. If I take this little piece on the end and I flip it over and I try to stick it on there, it won't go. It'll flip itself back over, and so the opposite pole connects on it. So no matter how small a piece you break of a magnet, it's still a magnet and has two poles. Okay, generally speaking, there is no such thing as a unipolar magnet with just one pole. It's got a north and a south. You break it into smaller pieces, you just have smaller magnets that have a north and south pole, but they still have a north and south pole. So you can't separate the poles or whatever, okay? Now, what we call the north pole actually means that it's attracted toward the north. So you could argue that technically it's the south pole of the magnet compared to the Earth's magnetic field, okay? And the south pole, or south seeking, is really the north pole, because it goes back to that. It's just arbitrary. We picked one, said that's North Pole on the Earth, and we said the other one's the South Pole. So now we do our magnets the same way. If we have a magnet that seeks the North Pole direction, we call it the North Pole. If we have one that seeks the South, we call it the South Pole. All right. I don't want to get real confused with that, but just there you are. Okay. Now, not only does the actual magnet itself have a force, but around it there's a force field, if you will, or a magnetic force field around it. And you've probably seen this if you played with magnets very much. All right, so just a second. In here we have some iron filings that have been swished around in there, and we have a magnet. Okay, now if I stick this magnet right here, I don't know if you can see that very good or not, but basically all the steel magnets are coming straight out from that. Okay, that tells me that that is the pole. If I put it on the side, I will see that they make a rainbow shape from top to bottom. So it goes from this side to this side, because this is the pole on top, this is the pole here, so it makes the connecting one. So you can tell by using a magnet whether that side of it is the pole or not. If the iron filings come straight out of it, that's the pole, because they come out straight. Then on the sides, they come down on the sides, and then they come to the other pole. So you make this kind of shape, and you've seen that before, and it's in your book. But you can actually tell, so which pole is it that way. All right, but anyhow, that's the magnetic field. All those iron fillings are still being influenced by the magnetic force of the magnet. Okay, and so that's the magnetic field. The magnetic field is just the area that is influenced. Now, if we could make this tall enough, at some point, the magnets, the iron fillings aren't going to be affected by it, because as distance increases, you exponentially decrease the force of the magnetic field. All right, but the magnetic field is the area where it is directly influenced by. Okay, technically we say the direction of the field is from north to south, so it has a direction to it. Okay, generally when we draw lines around the magnet, or you can look at this little cluster of iron filings, if they're close together, that tells us it's a very strong magnetic field. As they get farther apart, then you tell us that it's a weaker one. All right, now what makes magnetic? Why are things magnetic? Well, good question. Let's try to answer it. All right, let's talk about on an atomic level. How does this happen? Okay. Now, on the atomic level, we have electrons that are circling around the nucleus, okay? And we're really only worried about the electrons on the outer layer, okay? And say we have 8 on the outside layer, or well, let's just go with 4 first, okay? There's actually, say there can be a total of 8, but there's like little sub-rooms or sub-levels that can hold 2, okay? So it's kind of like if you had a house and each house can hold 2 people. Well, if you have 4 kids, and you throw them out in those 4 rooms, they're not probably not going to have 2 in this room and 2 in the other room. They're probably going to each want their own room, so they fill in all 4 of those rooms first. Then if you get a 5th kid, well, he's going to have to pair up with somebody, and then the 6th kid has to pair up with somebody else, and so on until they're all full. Well, that's the same thing that happens in the electron. They have these little subcompartments of 2 electrons. So first they fill in all those sublevels with 1 electron in each one. All right, and then if they have to, they start filling up the other ones. Now, if you look at them, the electrons are spinning one direction. All right, there we go, that rock group again. Didn't know they were so much scientific, did you? One direction, they're all going one direction. And when they spin a certain direction, that creates a magnetic field, which north is on one side and south is on the other. Okay, if you get another one on here though, they always spin in the opposite direction. Well, if they spin in the opposite direction, guess what? It reverses the magnetic field, and the south would be up here for that electron, and north would be down here. And so those 2 electrons are going to cancel each other out. Okay, electrons that have all 8 electrons in there, each compartment has 2 of them that cancel each other out, aren't going to have much of a magnetic field. Okay, but if you had 4 of them and they're all spinning the same direction with the north-south lining up the same direction, then you're going to have a stronger magnetic pull. So in the atoms that have a lot of these unpaired electrons are more likely to have a magnetic field. Okay, and some of those are iron, which is why most magnets are made out of iron. Also aluminum, nickel, and cobalt, or alnico. Sometimes we call it alnico, but basically that's Al, aluminum, Ni, nickel, and Co for cobalt. These all work well. So most magnets are some combination of those. Now, some of these super strong magnets we have, silver ones you'll see, sometimes very small but very strong. These are neodymium magnets, okay, and they're made out of an element way down at the bottom in the rare earth category that are called made out of neodymium and some other rare earth elements, okay. But basically, the elements, alnico magnets and iron, have a lot of these uncanceled electrons, and so they make very good magnetic materials. Now, if you look at the bigger part, atoms that are in the same area may all start lining up together. We call these domains. And normally, this whole area may all line up one direction, but guess what? These areas may line in different directions. And once again, the neighboring domains kind of cancel each other out. So even if you have magnetic activity, uncanceled electrons, unless these domains all line up the same direction, then they're not going to be attracted to a magnet. Okay, iron is particularly susceptible to that. Okay, and when they line up in the same direction, then you can make a stronger magnet. And it's easier to do that with iron and aluminum and nickel and cobalt and some other metals. And so that's why we usually make metals, those metals to make magnets, because we can get their domains to all line up in the same direction. One direction. Yes, there you go. They're just everywhere in science. Okay, who said there's no music to science? All right. Now, how do you get these in line? Well, you can tap them with a magnet or stroke the magnet. If you stroke a magnet over a piece of metal in the same direction over and over, it will pull these domains in line. Okay, and so we have what we call temporary magnets, and these materials will become at least a little bit magnetic. If you leave something in a drawer with a magnet long enough, a metal, iron or other metals sometimes, it will, being so close to the magnet for so long, it will eventually line up in the same direction as the magnet. All the domains will line up and it will become slightly magnetic. All right. Filing cabinets that set in the same spot for 10 or 15 years will actually be magnetized by the Earth's magnetic field and may have all their domains inside the filing cabinet line up in one direction. Okay. But if you drop the magnet very often, that will scatter all the domains. They'll be back here and it won't be magnetic anymore. That's why it's temporary. Or heating it. There's a temperature called the Curie, after Madame Curie. If you get past that Curie point, then the magnet domains will start going in every which way, and they'll lose that magnetic properties. Okay, like we said, iron is good to magnetize because it already has a lot of the uncanceled electrons in it, and it can easily be induced by another magnet to have a magnetic charge. We used to have iron bar magnets that we used, but they didn't always last very good because they were temporary magnets. We didn't have enough money, I guess, to buy really good ones. Okay, so what next? All right, so far you said, okay, yeah, well, I played with magnets. They're fun. They're a little part of the game and whatever, but why are they so important? I mean, it's not like electricity or something. Oh, but it is. And that's why magnets are all about electricity, okay? So magnets, without magnets, basically we don't have any electricity except for batteries. And most things that run on batteries aren't going to run very long unless we recharge them by plugging them into the socket and charging them back up with electricity. And you can't do that unless you have magnets, okay? And here's the why, okay? First one is what we call if you have a wire carrying electricity, the current is actually moving. Now, if the current's not moving, then you have no magnetic field, okay? So if I just have a cord like this one here, some magnets there. Okay, if I have a cord like this, it's not plugged in anything. So there is no current going through it, so there is no magnetic field around it. But if I plug it in and there's current flowing through it, then it has this magnetic field around it and a circle around it. Okay, and we talk about if the current's going this way, then the field goes this direction around it, or if it goes current's going this way, you stick your thumb that direction, then the current is going this way, counterclockwise or clockwise, depending which way it is. Okay, now that's fine, but it's not a lot of current. But scientists said, well, what if we coil this wire around? Well, if we coil it around, all this wire has circuit going, a magnetic field around it, and now these 1, 2, 3, 4, these are all reinforcing each other, and so you may end up with twice as strong of a magnet. And so it's like, hey, now we're getting somewhere, right? We have got a lot stronger magnet. Okay, for example, here is a wire flowing. You can see the circular magnetic field around it. Okay, this one is a loop, and you can see that they're getting closer together, so therefore it is a stronger magnetic. Now, if you have a coil, more than one coil, all these coils, this one has 6 coils. Now, you notice that they have a strong magnetic field, especially in the middle here, right down the middle, you get a pretty solid looking thing here. Okay, so when we talk about magnets, we're going to talk about coils because if electricity is moving through a coil, it creates a magnetic field. All right, so I've already get my thing going here. All right, so we have some batteries here, okay, which would give us electric current, right? We have 4 D-cell batteries, which is 1.5 volts, 1.5 volts, 1.5 volts, 1.5 volts. If they're in series, they all add together, which gives us a total of, drumroll please, that is correct. That is going to give us 6 volts, okay? So we have a 6-volt current here. All right, now, if I run it through this wire, okay, it would have a little bit of thing, but they've turned out that if not only do you have a coil of wires, but if you put a piece of iron through it, in this case we just put a nail in there and wrapped it around the nail, okay, it actually will become a stronger magnet. Okay, so we're going to hook this up to the batteries. Here's red to red and black to black, which should give us current flowing through. And if we stick the nail in here, let's see if we got much of a magnet. Well, I don't know if you can see that, but we do have one BB hanging on there. Okay, so we have what we call an electromagnet. Okay, why? Because it's only a magnet when the electricity is flowing through there and causing a magnetic field. All right, now someone says, well, obviously that's not very useful. All right, but someone says, well, let's up the ante a little bit. And usually when we talk about coils, this is what you'll see. If you look inside electrical things, you don't have to look very far before you'll see a coil of wires. Usually it's called magnet wire. It's been coated with enamel instead of the big insulator thing right here, which might get in the way of the magnetic field. So it's called magnetic wire, and this may be wrapped thousands of times around this coil. Okay, I don't know exactly, it doesn't say how many times, but it's many, many times, okay? So if I take this one and I hook it up, it's going through that current. It is creating a magnetic field, but it doesn't do anything until I put a piece of iron through it. But I've got a bigger one this time, so just like the thing. And when we stick it over here, you can see that it takes up many, many more. Now, the nice thing about an electromagnet is you can turn it on and off, which you can't do with a regular magnet. All right? If there's electricity flowing through it, it's a magnet. I guess I better hook that on instead of just touching it. Okay, if it's hooked up to the magnet, if you unhook it, it lets go. Okay, you've probably seen in the car movie, usually there's all these movies where someone gets tied up in a car and then there's this big smasher thing that's going to come get it, or with a big magnet. Well, that's an electromagnet. Okay, and they'll use that to turn it on. Okay, this is one. It's powered by a D-cell battery, 1.5 volts, not very much, you say. But we're going to take this piece of metal and this piece of metal and put it together. Inside of there are all the coils. Now, if I just hook that together, just the one battery, all right, and I try to pull this apart, it's not going to happen, okay? Supposedly, it can hold 200 pounds, which is about me. So if I were really brave, I would jump off the stairwell down here and see if it would hold me. But we're not going to take that chance, okay? But as soon as I take the thing off, the current off, then boom, it comes right apart, okay? And so electromagnets are temporary magnets that we can turn on and off, which is kind of handy, okay? Now, there's something else we want to talk about, all right? I've got a, let me see if I can get this where you can see it. I don't know if you'll be able to. Okay, I have a compass. Okay, hopefully I don't have any other magnets close to it nearby. But if I put this magnet, you'll notice that the white one points toward the magnet, right? All right, now I'm going to undo it, so there's no magnet now. And I'm going to switch wires. Okay, now what does that mean? That means the electricity is flowing in the opposite direction. Still the same amount of electricity, but just flowing in different directions. But what we'll notice is now, guess what? The white is stuck over here and the red is pointing toward it. So basically, if I switch to the direction that the electricity is flowing, I change the poles of the magnet. Okay? And so what used to attract the white now is attracting the red. Just the record, using this to find which direction is north would probably not be very good anymore because we've messed it up with magnets. You should never get magnets near your compass. Okay? But if we change the direction of electricity, it changes or reverses the poles of the magnet. And that is important. We'll talk about that later. Remember, alternating current changes 60 times per second. So it's constantly changing, and it's constantly changing the magnetic field around that wire that's carrying the electric current. All right? Now, what are some other practical applications of this? Well, let's do one more before we do that. You have probably seen, maybe not, something like this. All right, this one has a little dinger here, boing, that if I boing it, it hits the bell right there, boom, okay, like so. Now, if I touch the electricity from my volt battery point here, all right, it depends where I touch it. If I do it like this, I don't know if you can hear that. Okay, you can't see it. Sorry, but that's just the way it is. Okay, all right. Basically, if I do that, it creates a magnetic, but just once, and so it brings it in. Now, if I point it over here to these two posts here, not only does it do that, but then it keeps changing the direction of the current, and we get that instead. Why? Because now the electricity is changing directions, which changes the poles of the magnet. So it's attracted, it's repelled, it's attracted, repelled. It does that very, very, very fast, and you get the nice ring that we're all familiar with, okay? But if you just do it where it just creates a magnetic field once, it just attracts it, you disconnect it, and it lets go, and that's all it will do. But if you keep changing the direction of the current, it keeps turning the magnet on and off, and that gives you the ringer, all right? Just to summarize, we already talked about some of this, but to summarize a magnet, basically electromagnets are nice because you can turn them off, but you open the circuit and there is no current flowing, and therefore there is no magnetic field. The stronger the current, though, you hook it to more and more batteries, for example, I can get more and more batteries, then I can make a stronger and stronger electromagnet. Okay, it also depends on the coils. Like I said, when I had the the nail wrapped around here, about 20 wraps or so, it picked up a little bit. But when we got hundreds or maybe even thousands of wraps around the electromagnet, then it greatly increases. So the number of coils, as well as the amount of current flowing through it, have a great deal to do with the electromagnet. Now, basically, this is what they use in super colliders, or I can't think of the fancy name, but basically, they have particles, subatomic particles, that have positive or negative charges, and they turn on, turn off these electromagnets that keep attracting, and then when it gets there, they turn that one off, and the next one attracts it, and they speed up so fast, and then the particles smash into each other, and they go across the film, and they find all the little tiny particles. But basically, it's the same idea as turning on and off these magnets in order to speed up the particles through these big underground tunnels. Just for the record, they were going to build one in Waxahachie, just south of Dallas. Would have been a worldwide largest one in the world, but eventually it got axed because of budget cuts. Although, just found out this last week, there are some people that live in Paradise that came from France and Switzerland to be here originally for that project. They ended up staying, but there are physicists who came for that project before it got done. Anyhow, now the problem is, though, there's not a lot of resistance in this. Remember, if we have a circuit that doesn't have any resistance, light bulbs or other things using up some of the electricity, the current, then we're going to build up a lot of heat. Okay, and so the problem is there's the how big you make the electromagnet is limited by the overheating of the coils as the resistance builds up, and so they can overheat. But super magnets, okay, use superconducting coils, okay? So they're wires here. If you remember, those are the ones that let electricity go through with no resistance, okay? And because there is no resistance, they don't create the heat, and then they allow us to do neat things with them. And it also turns out superconductors actually repel magnetic fields. So if we had a superconductor, okay, and then we put a magnet on top of it, we can actually make the magnet float on top of it. Why? Because it expels, which we'll just say repel because for us it's the same difference, but it pushes it away from it just a certain distance. Okay, will not let it come to it, and so the superconductor pushes it away. Now if you have a train with either the magnets in it or the superconductors or vice versa, then it will just sit on top of that rail but never actually touch it. And bullet trains, all the really fast magnet trains, are just like that. They don't actually touch the rails. They hover above it because it's being expelled by the super magnets in it are being expelled by the superconductor, and so you have no friction, you have no bumps and jostles. If you've ever been on a train, even the newer trains, there's still a lot of jostling back and forth and stuff like that because of the wheels hitting the rails and hitting tracks and turning and stuff like that. And so you don't have any of that because you're not actually sitting on the rails, which is kind of a cool thing. All right. All right. So what else we need to talk about? Well, let's talk about this. Okay. Magnetic forces and moving charges. Okay. Moving charges are moving through a magnetic area, they will be deflected by the magnet. Okay, if the charges are not moving, they're staying still, then they're not affected by the magnet. All right, so we can use that, and also moving charges create magnetic fields which move things, and galvanometers, I wouldn't say galvanometers, but anyhow, galvanometers, all right, are different type of things that when electric current flows through it, it creates a magnetic field, and that magnetic field moves the needle back and forth. And so if it's a voltmeter, specifically, galvanometer just means it deflects, uses electric current to deflect a charge or create a magnetic to move a needle. So galvanometer is the general phrase. If we're using it to measure volts, it'd be a voltmeter. If it's a resistance, we call it an ohm meter. If we're measuring current, we would call it an ammeter. Okay, and most of the time nowadays, if you had an electrician come to your house, he's going to use this, which is a multimeter. Multi meaning it can do all of that. Okay, and so if anywhere I turn the dial, it can measure volts, it can measure ohms, it can measure amps, it can do all of it, just depending on where you dial it to. Okay, and so it makes it kind of handy. But that is basically, as the electricity goes through, it creates magnetic fields, and based on that, it causes it. Now, it doesn't actually obviously move. This is digital, so it doesn't cause actually a needle to move anymore. Okay, but it still is measuring that magnetic field, and that's what gives you the number up there. All right. Just for the record, we are protected. The Earth's magnetic field protects us from cosmic rays, which are highly charged particles coming from the sun that would cause a lot of damage. But the Earth's magnetic field repels them or causes them to deflect or go a different direction. Okay, so those moving charges are deflected or moved away from the Earth by the Earth's magnetic field, and that protects us. And if we didn't have a magnetic field, we would eventually feel the effects of that kind of thing. Now, all right. The next thing we want to talk about are motors and generators. Okay, motors and generators are related. They're very similar. Okay. A motor is something that takes an electrical source and uses it to create motion. Okay, and so it uses electrical energy to make kinetic energy, if you will. All right. For example, I have a motor here. This is a little tiny electric motor with a propeller, just so you can see which way it's turning. Isn't that cool? Okay, and we have it hooked up to a 1 volt, 1D cell power source. Now, if I hook it there, you will see that it goes this way, which if I did that right, is counterclockwise, I believe. Okay, but I know my picture's opposite of what I see happening here, so yeah. And I'm looking at it from the back side. But yeah, that is counterclockwise. Now, just for the record, if I switch these wires, which means now the electricity is going to flow the other direction, let's see what happens to the propeller. It goes clockwise now, or at least I think, depending on how you look at that. Okay. Now that may look counterclockwise to you because this is a mirror image. Anyhow, you get the idea. At any rate, it's definitely going the other direction. Okay? And so the direction of the current will also affect which way um, the propeller turns. Okay, which could be important if it was really in a model airplane or something and you got it turning the wrong direction, then it may not do very good. All right. Now that is considered a motor because we're putting in electrical. We put in from the battery electrical information, and it created kinetic energy. It uses magnets in there as the electricity flows. It uses magnets in there to cause it to spin. Okay. All right. More about that in a minute. Okay. But technically, all right, if I take this and do an amps. Okay, so we'll see if I can do this without dropping everything. Okay, so I have this hooked up to amps. Okay, if I were to spin the propeller, you can see that I get 10, maybe 13 milliamps. Okay, those are thousands of an amp, so not much. But if I spin the magnets, they will create electricity. And that's what a generator does. It's the opposite. We use gasoline or some other power source to move the magnets, and it creates electricity. Whereas a motor to use electricity to make the propeller move. Well, now we're making the propeller move, and we're using that to create electricity. And guess what? If I go the opposite direction, it still does it, but you get a negative reading. Why? Because the electricity is going in the opposite direction. Okay, that's the way it is. But it still works. It's still going to light up whatever it is or make whatever. All right, so basically that's what a wind turbine does. Okay, it spins and there's magnets inside it. As it spins, it creates, as a generator, it creates electricity. Okay, and so instead of having to physically turn this with gas or some other way, a gas motor like you would on a portable generator, a gas generator, you're just using the wind to spin it. Okay, and basically that's how all electrical plants work one way or another. Okay, they're generators. Okay, and what they do is most of them use steam and they force it through the blades of a turbine, and it turns the turbine, which turns some magnets, which creates electricity. Okay, and so that's kind of a cool deal. All right, that's basically it. Now the difference is, how do we heat up water to make steam? Well, we can use nuclear power, we can burn coal, we can burn natural gas. There's different ways. Nuclear power basically is just a way to create heat. Okay, once you get to the steam, it all works pretty much the same. All right, it's just a matter of how do you get the heat to turn the water into steam. Now, there are some things like solar cells, which I don't worry about right now, but we will later, that create electricity without doing that. But wind turbines, same thing. They're just turning the turbine using wind power. Okay, and so that's the difference between generators and motors. And so this motor can be turned into a generator if I just spin the propeller instead of using electricity to turn the propeller. All right, so they're just kind of reverse of each other. All right, this is Mr. McMurray, and we're going to look at a motor here. This is a very simple motor. Okay, not saying that it will always work. Sometimes it does, sometimes it doesn't. We'll see. Basically, it has a electric source, which is our battery, which are connected to these two posts on the side. Okay, and there's a magnet on the top. Now, if I just set it has a coil of wire, this is magnet wire that's coated with enamel. It has a little thing sticking out on one side here and one sticking out on this side over here. Okay, and they fit in these little things here. Now, you have a magnet down here. Based on the magnetic field from that magnet, it's going to make this loop rest at a certain position. And if I move it, it's going to go back to that same position based on the magnetic field of the magnet. But what turns out on these little side things, I have scraped off some of the enamel on each of these. Okay, and since I have scraped off some of the enamel, that means when the part without the enamel touches, now you have an electric current. And we know electric current creates a magnetic field, and it reverses this. So if this was being attracted like this before, now it's going to be repelled, which is going to push it away. Okay, now as it turns and it hits the enamel part, and there's no electric current. So now it goes back to this magnetic field, which is going to repel this part because it's just the opposite. It's going to keep doing that and spinning over and over. Now everything has to be just kind of timed just right so that when one part repels it, the other attracts it, and and that you have to get that in sync. Okay, now if we weren't using a battery, but we're using electric current, like AC, remember it changes direction 60 times per second. This is one reason why alternating current is great for making motors, okay? Because it automatically changes the direction of the current all the time, which changes the magnetic field, which makes it easier for it to spin. All right, and it kind of did for a while there, but it's still not 100% going like it should. It should just keep going forever and ever and ever on its own, as long as there's electricity flowing through it, and we're having a little bit of trouble. Of course it did. It worked fine before I turned on the camera, of course, but anyhow. Um, oh well. Okay. Looks like we're just not gonna. It's not gonna cooperate today. So let's see. Let me try one more time, facing me this direction, and see if that just shouldn't matter. It should be okay, but no. Something's a little bit out of kilter there. But basically, that's what's happening. Now, instead of scraping the enamel off different sides, some have brushes, and when the brushes touch, they conduct electricity through it, which changes the uh, um, magnetic field. So it just depends on how. There's different ways of doing the motor. Obviously, not like this, but basically that's the purpose of all electric motors. If you're not generating heat like in a hair blower or something like that, you're turning things like even in a hair blower, you have a fan that's going around, or a blender, or a mixer, or any of these things. I have a mixer here, which you can see, and basically you have some coils of wire in here. I don't know if you can see that very good there. And basically, you have a bunch of magnets, and it's going to cause this to spin. Then it's going to use these gears to eventually change that circular motion here until it gets to the mixer blades and causes them to turn around. So that's one of the main functions of an electric motor, is to cause things to spin. All right. However, this one is not cooperating today. So we may not get to see that. All right, let me just try something real quick. Turn that around. Just mess with it a little bit. Oops. Magnet just took off and said, I think I'll become part of your computer. Okay, hopefully I didn't mess the computer up. Okay, we'll put this back in here. And there we go. It's not doing great, but it is going around. It was going around there for a little bit. Okay, it was definitely more than what I did to it. It was kept going, but okay. You'll have to buy one of those. You can get them off the internet for about $3 or $4, and then experiment with it and become an expert yourself, and then we'll talk. Okay. All right. Now, part of what made this possible, the important thing about this idea of being able to spin things, we did that a minute, talking about the generator, that you can spin magnets and use that to induce electricity. Up until then, they could only use batteries, and they didn't have very good batteries at that, probably as good as we have now. And so there's not a whole lot you could do with batteries. You couldn't, run a car or something like you can now because we have better batteries. But they didn't have much they could do with electricity. So for it to actually be useful, there had to be a way to make it from scratch, if you will. And a guy named Michael Faraday in England and Joseph Henry in the United States about the same time, and they actually shared very nice. A lot of times scientists are not very nice people, and they fight over who discovered what first, and they hate each other and they hide each other's results. But instead, these two guys actually gave each other credit and said, "Hey, let's kind of share that." It's called Faraday's law, though, so I guess he got credit there. But basically, what they're saying is you can cause voltage, which we know voltage, okay, is caused or induced when a wire and a magnetic field move compared to each other. You can either have a magnetic field and spin a wire in it, okay, kind of like what we did on the motor over there, or you could take the wires and spin a magnet around them, and you could create electricity, okay? You may have seen these kind of things. This is a flashlight. You see the light coming out there, okay? All right, if I turn it on, then you can see it all the time. Woo, look at that. Okay, so it does that, but it does not run on a battery. Okay, it actually runs. It runs on a generator basically. So you have some wires in there. And to be honest, without taking this apart, I can't really tell. I don't know if they have a coil of wires and then they spin the magnets inside of it, or if they spin. But every time I push it down this handle, it spins that stuff in there. Okay. I don't know if you can see it there, but you can see the little white thing right there. You see how it moves. Yeah. So it spins that. And when it spins, either the magnet in the coil of wires or the coil of wires around the magnet, it will create current. Okay. And so basically, magnets are responsible for all the electricity we use that we plug into the wall. And even most of our battery things anymore are rechargeable, so we have to plug them back into the wall and get the AC current coming out of there in order to make them work. Okay. This is another one. This one, I don't know if you can see that, it has a little silver cylinder in the middle, and you can see the gold wire, magnet wire again, in the middle. And as you move that cylinder, the magnet, through the magnet wire, through the coil, as it moves through the coil, it will create electric current, and then that electric current can be used to, hey, turn on your flashlight. Okay, so you could use this out in the woods. You wouldn't have to worry about running out of batteries. Now, you would have to keep doing this, and if you're running from a bear or something, it might be hard to do that and move this back and forth at the same time, but it would work. Okay. Now, a fancier way of looking at that would be this machine. This is it's actually sponsored by the American Red Cross. You can turn it on there and then power it by just turning it. You can tell it has a lot harder turning, so it probably creates more electricity. And this one actually, if you look on the side, has a USB port and a mini USB port, and so you could actually charge your phone. Now, I've never tried that, and how long you would have to turn it to charge up your phone, I suspect it would be a while, but theoretically, you could do that. All right. Now, another thing we also have here, this is it used to be the wheels or axle off an electric car. Normally, you have a motor right here in the middle. I think you can see the end of it right here. Okay, and that's a motor. Electricity would come through it, and it would cause the wheels to turn. Okay, well, one of my students many years ago, was in, I believe, in 6th or 8th grade, said, "Hey, what if we did it the other way around?" And he has put a Christmas tree light and welded it onto the battery. So now, if you spin the wheels, it becomes a generator instead of a motor. He's using it as a generator, and it actually makes enough electricity by spinning the wheels to turn the light. Is it going to power your whole string of lights on your Christmas tree, which I'm sure you've already got up because it's already past Halloween? So, surely you put it up already. That's just getting ridiculous. But anyhow, but it is the same idea, the generator, okay? And generators, like I said, we're using mechanical or kinetic energy and creating electricity, whereas a motor uses electricity to create mechanical energy and stuff like that. Now, in electric cars, they actually, it can act as, the battery can act either way. If you're speeding up, accelerating, or you're climbing, so it draws off more current, it uses current from the battery and acts like a motor, uses that energy, electricity, to turn the wheels. But if you're coasting or going downhill or braking, it will actually act as a generator and use that spinning motion of the wheels to recharge the battery. Okay, and so keep in mind, generators do not create energy; they can only convert it. Energy is not created or destroyed, but they can take the mechanical energy of the car and change it, like a generator, and change it back into electricity. Okay, and so that's kind of a way to help you get farther along. All right. I'm sorry. Back to induction. Sorry, I didn't say. Faraday's law said basically the more coils you have, then you will directly get more voltage created. Also, the stronger the magnet, okay, the more loops, and the stronger the magnet, and how fast the magnet goes back and forth. Just like this thing here. If the more times I can shake this back and forth, then the faster it goes back and forth through there. The rate at which the magnet is moved around the wire, or the wire around the magnet, is going to increase the amount of electricity created. Okay. Now, unfortunately, as you get more and more electricity created, it goes through those wires to light up the light bulb. It creates more resistance, and then that makes it harder to make the whole thing work. Okay. But keep in mind, this is also why if you go through the metal detectors at the airport, they have magnets. If you move through that, if you have the metal, it creates an electric current. You're moving through it, a moving thing, and so it will actually create electric current, and that will send a little burst of electricity and it sends the alarm off. Okay, some places at stoplights. Some have cameras that see if someone's there or not, but others you see little strips in the ground where they dug out and put something down there. Well, basically, it's magnets. When the metal of your car flows through that, it creates an electric current, and if it does, then that tells the light that you're there and you need to turn left or whatever, and eventually it will make that happen. Okay, the magnetic strip on your credit card. I'd show you mine, but you'd probably want to steal the number or do something bad, and I don't have enough money for that. But anyhow, we'll just use my driver's license. All right, it has magnetic strip. When you move that through the machine to use your credit card, okay, it's a magnet moving through um, wires, and that creates electric current, and it uses that to read the information off of your card. Okay, so those are just some examples of induction. We're using moving magnets or moving wires in a magnetic field to create or induce a current. Okay, all right, just a second, we'll look at another example of that, and then we'll be on our way. All right, now here we have an aluminum tube. Okay, I can put magnets up against it, and you'll notice it is not magnetic. Okay, these are also not magnetic. Okay, these are a piece of metal. So I'm going to put a piece of metal in here, and I'm going to drop it, and we'll see how long it takes to get to the other end. Let it go. Okay, if I'm fast, I can almost catch it, right? That's about all I can do. All right. So now we're going to try something a little different. We're going to take a little magnet. All right. And we're going to drop it through this tube. Okay, so I'm going to drop it and then catch it. Ready, set, go. Whoops. Hey, sorry about that. Didn't go in. Sorry. There I go. 1, 2, 3, go. And we're waiting. And we're waiting. And we're waiting. Well, what happened to it? Interesting question. Okay. Yeah, let's try this. Okay, we drop the thing through there again. That knocked it right through. Okay, sorry, I got too skinny at one. Sorry, my bad. All right, let's try it with a little wider one. I meant to do it with this one. Okay, guess it's a little wider. Sorry, try it again. Okay, so here we go. Drop it. Go. And if you look down there. All right, it eventually comes out the bottom, but it takes a while, right? Question is, what's happening here? This is a magnet, yes, but the aluminum is not magnetic, so it's not that. And in this case, that wasn't the first one, sorry, I put it through the wrong one. It wasn't because it's stuck. If you look down there, which you can't see, but if you were here, I'd let you look through it. Boom, there it is. It takes it forever to go down. Okay, well, let's try something else. Hard part with working with magnets, it's hard to keep the magnets from attacking. Okay, so this is another one. This one we have copper. Copper is also, if I put this magnet to it, nothing happens, okay? But if I'm going to drop a piece of metal here. I go 1, 2, 3, and boom, it comes out the bottom. About as fast as I can try to catch it, okay? But now this time we have put a little strip here. Hopefully you'll be able to see this. This is a little strip of paper that has little metal pieces embedded in it, and you can kind of see the magnetic field. So I'm going to drop the magnet. This is a ball shaped, same as the other one almost, but it's going to go down there, and let's see if we can see the little magnet showing. I don't know if you can see that. There's a little line going down there, and you can see it coming down, 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 and then finally coming out. Okay, now why does it take so long? Well, we have a magnet moving through, so it's a moving magnetic field, and we know if there's a moving magnetic field, it will create an electric current, and it does. And so as it's going down here, it creates an electric current because copper and aluminum will conduct electricity. Okay, and so it creates electric current, and it begins to go around there. But as it goes around there, electric current creates a magnetic field, and that magnetic field is in the opposite direction. The north and south has been reversed to the magnets going down it. So you have this magnetic field created by the electricity pushing up and the magnetic field of the ball that's falling. And so it takes it a long time because you've got two forces that they don't cancel each other out, but they do. Take a long, long time to go. Now, this is used in various ways. One way is on roller coasters. When roller coasters come in, uh, they have magnets that create a, a current in the rails, and that current in the rails creates a magnetic force going the opposite direction, and that's what allows you to come when you're coming in from. When you slow down that last little bit when you stop, and that don't run over people and just go shooting out onto the roller coaster again. That's these. Now these are called eddy currents because the magnet produces it, and then the magnetic field pushes back against it that slows it back down. Okay, kind of cool stuff. Okay, let's do one more time. We'll do it in aluminum. We'll make sure this won't fit. Yeah. Okay, so I'm gonna drop this in, and let's just time it. On mark, get set, go. 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000, 11,000. 12,000, 13,000, 14,000, 15,000, 16,000, 17,000. No, and there it finally came out. Okay, so it took almost 17 seconds for it to go down. All right. On the other hand, if we put the metal ball through, here we go. Set, go. 1,000, whoa, 2,000. So it could really slow it down quite a bit from 2 seconds to about 17 seconds. Okay. So those are eddy currents, and they're caused because the magnet moving through there, moving magnetic field, creates an electric current in the pipe. The electric current in the pipe creates a magnetic field pushing the opposite direction, and because of that, it goes very, very slowly. It looks like it's levitating almost. If you look down the tube as you do that, it's really cool. It's just kind of drifting slowly down to the end. All right. Now, it turns out that not only do actual electric currents moving through a wire or magnetic fields based by big solid magnets, this can also happen to magnetic fields or any electric field, even if there's not actual there's wire or not, and so are metals involved. Okay, and so basically, if we have a electric field in space, some kind of particle that vibrates and sends off a changing electric field, it also creates a changing magnetic field. And so you have this electric field that's changing or vibrating and sending off electrical vibrations. It's also creating a magnetic one, like one's going up and down like this, the other's coming toward you and back like this at right angles, and they're both going together. And so we call these electromagnetic waves, okay, because it's caused by vibrating electric fields, which creates vibrating magnetic field, which creates more, and they just kind of feed each other as they go along. And these are what we call electromagnetic waves. Now, and if there's something that is changing its electric fields, then it will create these changing magnetic fields, which create more changing magnetic fields, and it will carry this energy through this, and they're inducing each other. And this is what we call electromagnetic waves. What are electromagnetic waves? They're anything from radio waves, AM and FM radio. X-rays are very high frequency vibrations. Gamma rays also very high frequency. UV, not quite as fast as those, but then the light that we see is basically electric and magnetic fields vibrating. So once again, is magnets important? Yes. We couldn't see things that have light. We couldn't do x-rays. We couldn't listen to radio. Microwaves, infrared, the ones that warm your food after, if your food gets ready, but the other person who orders not, they stick it under the infrared waves. These are all electromagnetic waves. Okay, and they depend upon magnetic fields that vibrate as well as electric fields. Okay, and so even though we hear all about electricity, we know how important electricity is, keep in mind it all comes from magnets. Okay, and so not to mention light and radio waves and all those kind of things that wouldn't exist without magnetic fields as well as electric fields. All right, I think that's about everything then. Hopefully you will get your questions turned in, take your quiz, and it's that time again. The good news is we only have 3 chapters on exam number 3 and exam number 4, but since this is the 3rd chapter since we've had an exam, we are ready for another exam. All right, so make sure you take care of that, exam number 3. All right, so you do your questions, do your quiz on chapter 11, and then we'll be ready for a exam number 3. Good luck.